morning, everyone. The same announcements as the lecture before, the exam material and the mechanisms. And here are the mechanisms included in the exam, 3 of them. So that's for your own kind of notes. I'm gonna wait until everyone gets seated. Okay, so this is also a reminder that if you're taking the exam in UMass, you should show up outside the Gen Chem lab at 9:20 and wait outside. You need your UMass ID. If you're taking it in a Proctor Center, then you need to show up to the Proctor Center on time and definitely not to use Internet Explorer. So yesterday we discussed the alpha alkylation, or the alkylation of the alpha carbon of a carbonyl, and all the examples we discussed were for a monoketone. And I mean by a monoketone that there was only one carbonyl or monoaldehyde, one aldehyde or ketone in the molecule. Let's just go a quick review over that. So let's say I have this in here, and then we added as a first step LDA-THF minus 78 Celsius, followed by the R prime X. We ended up with the R prime on the alpha carbon, as long as the R prime X not phenyl. If it is a phenyl, no reaction. If it is a vinyl, it will be no reaction. Now, if it is tertiary, we prefer not to have a tertiary. If it is a tertiary, it will be elimination. The tertiary alkyl halide will be eliminated to an alkene. We also discussed secondary is 50-50 yield. So to make it easier in an exam, I wouldn't give you secondary so that not to trick you. So either primary or one of the limitations, and you have to figure it out. Also, we discussed the fact that we can have a preferential kind of to one alpha carbon over the other, which is kinetic versus thermo, and the example that we went over is this one. If I use LDA THF minus 78 Celsius with CH3I, this is gonna go to the less sterically hindered carbon of the two alpha carbon, and this is the kinetic. That's mean to the less sterically hindered, the one that forms faster. While if I use NaOH or OR minus followed by the iodomethane, it will end up on the more crowded carbon, which gives the more stable enolate ion, which we consider the thermodynamic, and we can preferentially choose one over the other. We also discussed about the bromination of the alpha carbon under acidic and basic conditions. So today we're gonna go do some practice on those concepts. Then we're gonna move on to the compounds that have more than one carbonyl and how we're gonna handle that. So let's get started with the first example in here. So the question is, figure out the steps needed to go from the starting material to the end material. So stop the video and do it. So as usual in multi-step, we're comparing the starting material to the end material, trying to map it to see which part of the starting material is in the end material. So we can map this part in here to this part. So clearly we have a carbonyl. We change the OH into a ketone, a secondary alcohol in here into a ketone, which is not that hard. It's an oxidation thing. Then we have a methyl on the alpha carbon of that ketone. So that's kind of just answer the question itself. That is, at first I need to change the alcohol to a ketone. The question is, should I do that before or after adding the methyl to the alpha carbon. So clearly we can't add we didn't learn that we can add alkyls to the alpha carbon of an alcohol. That doesn't happen because the alpha hydrogen of an alcohol is not acidic in the first place because it doesn't have the resonance structure if we deprotonate it. So our first step is the oxidation of that alcohol. So we have a secondary alcohol, we need to have it as a ketone. It's an oxidation reaction in which we can use chromium H+, or sodium dichromate H+, and that would result on this one in here. Now looking at this ketone, it has 2 alpha carbon, each has at least 1 alpha hydrogen, but the molecule is unsymmetrical. This is bring us to the question, is the kinetic or the thermo the one that I want in here? Every time you look at a ketone and it is unsymmetrical in the sense of the alphas carbon are not the same or not equivalent, this is where it's gonna be the question, is it a kinetic or thermo? Because if I wanted to favor the kinetics, it's different reagents than the thermo. So looking at it, I can see that the methyl or the new R prime that I'm gonna add to the ketone is added to the more sterically hindered or the more substituted carbon. So that's a thermodynamic. That the addition is added to the carbon that is more crowded or more substituted, so that it's more technically right, substituted alpha carbon. So we know that if I want to favor the thermodynamic, I use NaOH or R prime O minus, and I'm putting R prime O minus. It could be methyl, ethyl, and this is why I'm keeping it kind of open. Now, how to figure out what is the alkyl halide I'm adding? I have to compare this to this one. I can see that I added a methyl. So iodomethane, and I should remember that there are limitations for the alkyl halide. It couldn't be tertiary, it will undergo elimination. It couldn't be phenyl, it couldn't be vinyl. Clearly in here it's iodomethane, so it's not even primary, it's just iodomethane. So that's not part of the limitation, and I'm favoring the thermodynamic. Does this make sense to you, where we're gonna use the thermo over the kinetic and how to favor it? Now I'm gonna stretch the question a little bit more. What if the question is to prepare this one in here? I'm adding one more carbon and ethyl so that it's more clear. So how can you prepare that? Now looking at it, the ethyl is added to the alpha carbon that is less sterically hindered. To favor the less sterically hindered, which is the kinetic, we use LDA as a reagent. So LDA THF minus 78. Now the second thing is the alkyl that I'm adding. In here, the alkyl I'm adding is this one in here, which is ethyl. It can be iodine or chlorine or bromine, but I'm putting iodine in here. It's a primary, not tertiary, not phenyl, not vinyl, so the reaction should take place, and this is the kinetic. This one in here is the thermodynamic. Does this make sense? And you're gonna see this equation as multi-step in a couple of different ways. One time favoring the thermo, one time favoring the kinetic, but it's always gonna be the same idea. Does this make sense? Questions about any of the steps? Okay, let's do more. So the question in here is, what is the major product of the following reaction? So stop the V. The most popular answer is D, but not with that big of a margin. So D is the right answer. So the first step in here is LDA THF minus 78. So I'm gonna go over it in details. So the LDA, it's gonna deprotonate the less sterically hindered carbon, alpha carbon that has at least one alpha hydrogen. So this is an alpha carbon, this is an alpha carbon. This one in here has no alpha hydrogen. And I'm gonna redraw this so that you can see that that's the case. Look at this carbon, 1, 2, 3, 4 bonds, no alpha hydrogen. A benzene ring connected, an aryl ketone, that alpha carbon has no alpha hydrogens. So this is the only one that has the alpha hydrogens. So this is the one that's going to be deprotonated. Nope. So this is the one that's going to be deprotonated in here. Now the next step is the addition of this in here. So we learned that the alkyl halide has limitation, and the R prime X not tertiary because it's gonna undergo elimination instead of substitution, not phenyl, and not vinyl. Let's look at this one. The Cl is directly connected to the C double bond C. This is a vinyl chloride. So the reaction gonna stop right here. This gonna pick the hydrogen back from the LDA and go to the starting material. So in other words, this is the limitation in an example. Now, this is what I find often that the misconception is the student not able to identify that this is a vinyl. The easiest way to identify something is a vinyl when the Cl or the Br is directly connected to the C double bond C. This can be an open chain or a cycle, something like this, or cycle of cyclohexane. All of this is the same. Is this a vinyl? So if I put this as the reagent, would the reaction take place? Yes, because this is an allyl, not a vinyl. And the limitation is only for the vinyl and the phenyl definitely. Does this make sense? Okay, let's go to the next one. Again, the question is, what is the major product of the following reactions? Stop the video right here. And D is the most popular answer, and I can see why you chose D. But the right answer is C, and we'll discuss this. So, first of all, let's talk about the obvious, that the alkyl halide is a tertiary alkyl halide. It's part of the limitation, which is that a tertiary alkyl halide, instead of undergoing substitution, it undergoes elimination. So it's not gonna take the substitution, not gonna take a place. So it's not gonna be B or A. What's gonna happen is that the first step, the obvious, which is the formation of the enolate ion. Now in the second step, instead of that enolate ion kind of substituting the Br in a substitution reaction, instead it's gonna eliminate, it's gonna come and eliminate the hydrogen, undergo an elimination reaction where it eliminates an H and the Br from the alkyl halide, resulting in the alkene instead of what we kind of expected, which is the alpha alkylation. And this is why I kept saying that phenyl and vinyl, they're gonna give no reaction, no substitution, while the tertiary will undergo elimination. Now, definitely the elimination is the elimination of a Br and a hydrogen from the from the neighboring carbon. In here, all the neighboring carbons are equivalent and they will give exactly the same alkene, but if it gives different alkene, the alkene that is more substituted is the major. Does this make sense, guys? Okay, so I'm gonna go and circle the right answer in here. So definitely not substitution, it's an elimination. Let's do, so with these 3 slides, add to that a phenyl and a phenyl as an example, and those are the limitations in an example. So in all of the other examples we discussed between last lecture and today's lecture, we dealt with a monoketone with only one C double bond O in the molecule. Now, we're gonna see examples where we have 2 carbonyls. We call it a dicarbonyl compound in the compound. Let's start with this simple question. Which hydrogen is the most acidic between A, B, C? And these are A and B because the molecule is symmetrical. So go ahead, stop the video. C is the right answer. So every time you're asked about the acidity, it should be like a method that you're always gonna use. Draw the conjugate acid, the conjugate base, and the one that is more stable is the most stable, represent the most acidic. Now, if I draw the conjugate base of the C, I'm going to go directly to the C one since we figured out it is the most acidic. We'll find out that it is the most acidic out of all the other conjugate base. One, because the minus, the carboanion is between two carbonyls. So that's one stability. The withdrawing group that stabilizes the carboanion, but that's not all. That minus, that carboanion is involved in resonance both to the right side and to the left side, in another resonance structure to the other side. So as you can see, it's stabilized by resonance and it is between two carbonyls. Actually, always the alpha carbon between two carbonyls is much, or the alpha hydrogen between two carbonyls is always more acidic than the alpha carbon of a monoketone, and that's always the case. So in this case, which we're gonna deal with for the rest of this chapter, is an alpha hydrogen between two carbonyl. Those we don't need usually LDA for that. We just use ethoxide or OH minus for that case because it's much more acidic than a monoketone. And this is what we're gonna go over now. Now, the usual precursor that we use is what we call malonic ester, and this is the structure of malonic ester. So from now on, you need to know when I say malonic ester to understand that this malonic ester is a CH2 between two C double bond O of an ester. The ET in here, ET represent a CH3CH2. Now, the same as it is a very typical steps to alkylate the alpha carbon of a monoketone, which is LDA followed by R prime X. It's also, there is a very typical, three typical steps to alkylate and produce something from the malonic ester. So let's start with the first step, which is using the sodium ethoxide. So just note that we're not using LDA in here, we're using sodium ethoxide. The result of that is the deprotonation of the most acidic alpha hydrogen, which we just learned from the slide before, that it is the alpha hydrogen between the two carbonyls, not any other alpha hydrogen. We're using Y ethoxide because it's a strong enough base to deprotonate that acidic alpha hydrogen. Add to all of that we don't want LDA, which is bulky, to deprotonate that alpha hydrogen in there. Now, the very next step is using R prime X. What do you think are the limitations for that R prime X? Not vinyl, that's right. In other words, exactly the same as before. Not vinyl, not phenyl, and not tertiary. So the next step is this, substituting that. Now, what's different than the monoketone is the next step, which is the addition of H3O plus heat. As you can see, this is a diester, two esters. Now, we learned if we have a diester and we add H3O plus heat, that is a hydrolysis reaction of the ester to go back to carboxylic acid and alcohol. So what's going to happen next after the addition of H3O plus is two ethanol molecules, so this and this will leave, and the diester will be hydrolyzed to a dicarboxylic acid. But the reaction doesn't stop there. In here we have two carboxylic acids that they are beta from each other. We learned in chapter 20 that when we have a dicarboxylic acid that they are one carbon from each other, if I heat them up, they decarboxylate. That means one of these C double bond OOH will leave as a CO2. So the end result of that is one of the carboxylic acid, whether the left one or the right one, will leave as CO2 plus so I'm going to end up with a carboxylic acid, CO2, definitely from the step before the ethanol. So that's because of the heat associated with the H3O plus heat. So the first step is a base followed by R prime X, which is not very different than the monoketone. The third step is this one that's slightly different because I'm adding H3O plus heat, I'm hydrolyzing the ester and decarboxylating one of the carboxylic acid into a CO2. So what I'm gonna do is I'm gonna re-summarize all of this because the answer is typical for this. The answer for these three steps is very typical as we go. So if I summarize the whole reaction, anytime we're starting with a malonic ester, and I do the very typical three steps, sodium ethoxide, followed by R prime X, followed by H3O plus heat, I'm going to end up with 2 moles of ethanol if these are EOT. If they are methoxy, 2 moles of methoxy. CO2, when one of the carboxylic acids going to be decarboxylated, and a carboxylic acid like this. In other words, if we want to use what is mapping, this part of the molecule is this part of the molecule with the OET replaced by an OH. Whatever is added is to the alpha carbon of that, and it is the R prime from the alkyl halide. In other words, you can predict the answer without going through the steps. If you have these 3 very typical steps, all that you have to think about that you're going to end up with carboxylic acid and an alpha carbon. The alkyl halide, the R prime of the alkyl halide, as long as it isn't tertiary phenyl or vinyl, gonna be on the alpha, and then CO2 plus ethanol. Does that make sense to you guys? And just with the slides, with the upcoming slides, we're just gonna change the R prime X. So this is if we start with the malonic ester. Questions about any of the steps? Now, another precursor that we start with, and I mean precursors, that means it's going to be very typical, is what we call acetoacetic ester. Aceto, because we have an aceto, which is a methyl ketone, an alpha carbon between it, then an ester. So the difference between this and the malonic ester has 2 esters on the sides and an alpha carbon in between. Here we have a methyl ketone, alpha carbon, then the ester. Also, very 3 typical steps. A base, actually, let me repeat, sodium ethoxide, R prime X, and the third step, H3O plus heat. So if you think about it, exactly the same 3 steps as the malonic ester. The first step, sodium ethoxide. I hope that all of you are predicting that the ethoxide gonna pick the most acidic alpha hydrogen. If we look at all the hydrogen in this molecule, the hydrogen that is between the 2 carbonyl gonna be the most stabilized conjugate base. Its conjugate base gonna be the most stable. So we formed the carboanion or the enolate form. R prime X, again, the R prime X, not tertiary because it will eliminate, not phenyl, and not vinyl, whether it is cyclic or open chain. So also, as predicted, the R prime gonna end up on the alpha. Then the last step, which is H3O plus heat, is changing the ester into a carboxylic acid. It's not gonna change the carbonyl of the methyl ketone into a carboxylic acid. So the result of that is CH3CO CH R prime, and this changing to carboxylic acid plus 1 ethanol. In the case of malonic ester, we ended with 2 ethanol because we have 2 ethanols, 2 OETs from both sides. Now the heat itself, which is part of this molecule, part of this step, it's gonna decarboxylate. If I have 2 carboxylic acid that they are 1 carbon from each other, one of them will decarboxylate, will leave as CO2. If I have a carbonyl and a carboxylic acid that they are 1 carbon from each other, only the carboxylic acid we're gonna decarboxylate. It's gonna leave as CO2. So the end result of this is a methyl ketone. A methyl ketone because I have methyl and C double bond O. This is the alpha carbon, which is this one in the starting material, and the R prime is the alkyl halide. What I'm gonna do next is summarize it. If you see the 3 steps to directly predict the product. So if I'm starting with acetoacetic ester, and I do the very typical 3 steps, sodium ethoxide, R prime X, and H3O plus heat, the result of that is this part, the methyl ketone with its alpha. This part in here gonna stay as is. On the alpha, the R prime from Rx will be attached, plus a CO2, which is the decarboxylation of the ester that's going to end up being a carboxylic acid and an ethanol molecule. So it's very predictable. If I only do these 3 steps for a malonic ester, I'm ending up with a carboxylic acid. The carboxylic acid is there and its alpha carbon is the same with an R prime connected to it, plus CO2 and 2 ethanol. If I start with acetoacetic ester, I'm always gonna end up with methyl ketone plus CO2 plus ethanol. The methyl, the C double bond O, the methyl, the C double bond O, and the CH2 are exactly the same, and the alpha carbon has the R prime from the alkyl halide. Again, the alkyl halide shouldn't be tertiary, phenyl, or phenyl. And by the way, this is the whole chapter. We're done from the idea. We're just gonna try different compounds. Now this idea, the methyl ketone can be open chain or cyclic. The malonic ester can be in the form of 2 esters in a cyclic compound or open compound, but the idea is exactly the same. Find the most acidic alpha carbon, which is between the 2 carbonyl, add the alkyl halide, add H3O plus heat. Now, most of the time, we don't only do these 3 typical steps. After the 3 typical steps, like in here, this is a methyl ketone. We can do some of the reactions from chapter 19, like Grignard, reduction, oxidation, name it. Any reaction we learned from chapter 19. For the carboxylic acid that we get from the malonic ester, after the 3 steps, we could esterify it, we could change it to amide, to acidic chloride, to any of the reactions we learned in chapter 20. Okay, then we're done from the concepts. Let's do some reactions. So in here, we're starting with the malonic ester, and these are the steps we're doing. The question is, what is the end material? So stop the video and do it yourself for those who are. So in here, there are more than the 3 typical steps. So let's take it one by one and see what's gonna happen. So sodium ethoxide. The idea is the deprotonation of the most acidic alpha hydrogen. This is the most acidic one. There is no change in that. Because it is between 2 carbonyls and it is stabilized by resonance. The next step is the addition of the CH3I. So the alkyl halide is not tertiary, not phenyl, not vinyl. So the reaction will take place, and that would result on the following: the methyl and the ester. But usually at this step we add the H3O plus heat and we end up with the carboxylic acid. But sometimes we don't stop there, and as long as there is another alpha hydrogen, we can deprotonate it and add one more alkyl. So the addition of sodium ethoxide will deprotonate the second alpha hydrogen, resulting in the carboanion and the next step is the addition of the iodoethane. It's a primary, not tertiary, not phenyl, not vinyl, so that would substitute it. So in here we added two substituents to the alpha carbon. The methyl and the ethyl. And I'm keeping the color coding so that you can see where each is coming from. The last step, which is the H3O plus heat, where two ethanol molecules gonna form CO2, one of the carboxylic acid that forms gonna be decarboxylated, and the other part gonna end up with carboxylic acid. This is the alpha carbon. Now to it is attached the methyl and the ethyl, and it picks a hydrogen during the mechanism. So the end result is we ending up with the carboxylic acid. The alpha carbon is still the same, and to the alpha carbon, the two alkyl halides that are there. This is typical that sometimes as long as the alpha carbon has two alpha hydrogen that we can pick, we can do it in these steps: sodium ethoxide, iodomethane, sodium ethoxide, then the alkyl halide. The rules are still exactly the same in the sense of limitation and what we should use. Make sense? Okay, let's go to the next one. So the question in here is select the ketone below that can be prepared starting from acetoacetic ester. Since we just started the concept, I'm gonna give you the structure of acetoacetic ester, but later on I'm assuming in the exams all that you know what is the acetoacetic ester and what is the malonic ester. So the question is, if you start with this acetoacetic ester, pretend that we're gonna do the very three typical steps. Which of the following can be prepared starting with acetoacetic ester? Stop the video right here and try and do this yourself for those who are in. And I have C to be the most popular answer. C is the right answer. So in here, it's just kind of concluding what exactly I can prepare from this acetoacetic ester. We learned that if I do the very typical three steps, which I'm writing, what we gonna end up with is this part gonna be in the product. The methyl, the ketone, and the alpha. To the alpha, to whatever is connected to the alpha in the product is the alkyl halide, is the R prime from the alkyl halide. So this is the methyl, this is the alpha, methyl, ketone, alpha. So whatever left that I'm circling in green is the alkyl halide that I have to use for the prep of this one. And if we look at it, is a tertiary. And we said that tertiary is one of the limitations of the acetoacetic ester and the malonic ester. So I can start even with malonic ester and end up with all of these instead of a methyl ketone, a carboxylic acid, and the result is exactly the same. Does this make sense how I analyze it? Let's go to B. This part 1, 2, 3, the methyl, the C double bond O, the alpha. So this is the part coming from the acetoacetic ester. Whatever left is the R prime from the alkyl halide because it's connected to the alpha. Phenyl. Phenyl are also no, we cannot use neither tertiary nor phenyl nor vinyl. So I can add one more example with a vinyl. In the very last one, this is the methyl, this is the ketone, this is the alpha. So here we are. Whatever left that I'm circling in green is my alkyl halide that is coming from the R prime X, and that can be X. So that's a primary. This is an ethyl halide. that's a primary, the reaction will take place. You're gonna see this question in OWL in the practice and in the exam, whether you're starting with malonic ester or with acetoacetic ester. In other words, I'm asking you in practice if you know what are the limitations. The phenyl, not tertiary. Primary is okay, allyl is okay, benzylic is okay. Make sense? Okay, let's do more. The question is again, what is the end material of these 3 steps? Stop the video right here. And okay, so I'm going to start with the first step, which is adding the sodium ethoxide. We have 2 carbonyls, so the most acidic alpha hydrogen will be between the 2. 1, 2, 3 bonds, so there is at least 1 alpha hydrogen. So it's going to be the deprotonation of that alpha. So the next step is adding this benzyl bromide. So this is the pH is benzene ring, CH2Br. Is this part of the limitation, a benzyl? No. The phenyl is. If the halide is directly connected to the benzene ring, it is. But if it is a benzyl, 1 carbon that is attached to the benzene ring, this is a benzyl, the reaction will take place. So the next step is, I'm going to refer to the benzene as pH just to save some space in here. The last step is H3O plus heat. Think about it, this is the same as the methyl ketone, in which the ketone stay as is, yet the ester gonna go to the carboxylic acid, then undergo decarboxylation. So it's gonna be CO2, which is decarboxylation of this, the ethanol, and the end result is the ketone. It's alpha carbon, and whatever is attached to it is from the R prime, which is in this case is the benzyl. Does this make sense? Questions about the steps done here? So what I'm trying to show you in this, that we can start with a methyl ketone or even a ketone in a cycle, and then have an alpha and an ester. So the steps are the same. It shouldn't be always methyl ketone or malonic ester. Okay, now the question in a different way. We're starting with acetoacetic ester, ending up with this compound. The question is, what are the steps needed, the reaction needed for this to be achieved, definitely in a good yield. So stop the video right here. Okay, so you're starting with acetoacetic ester, ending up with a methyl, a C double bond O, and a CH2. So we know that usually the three typical steps, starting from acetoacetic ester, we can map that this part of the molecule gonna end up being the same. Whatever left is gonna be my alkyl halide. So the steps that are needed is sodium ethoxide to deprotonate the alpha carbon in the acetoacetic ester. Whatever left in here is this. So this is gonna be my alkyl halide. I always have to keep an eye that it isn't one of the limitations. It isn't phenyl, vinyl, or tertiary. Followed by the last step, which is H3O plus heat for the decarboxylation. Okay, so that's how we figure out the 3 steps from the starting material. Okay, let's try another one. So we're starting with malonic ester. We're doing 3 typical steps. And in here, just I need to add that the sodium ethoxide, we have 2 equivalents. So for each 1 mole of this molecule of the malonic ester, there are 2 equivalents of the sodium ethoxide. So stop the video. Okay, so starting with the sodium ethoxide, the first equivalence, what's going to happen is that the very typical step, the deprotonation of the alpha carbon, which is the most acidic. So we're going to end up with the minus the carboanion there. Now, the only difference about this alkyl halide from any other case, it is a dihalogen. It has two halogens or dialkyl halide, two alkyl halides in the same molecule. So here, where is the... So I'm going to redraw that. And as you can see that the two BRs are 1,4 from each other carbon-wise. So, and they are symmetrical. This is a primary, this is a primary. They are symmetrical, so there isn't a preference for one over the other. So I'm gonna also label this as A, B, C, D. So we're gonna end up in here with what we usually expect. So this is the A, B, C, and this is D. That is connected to the BR. And I highly recommend that you do so if you're still a beginner, especially when we have something like this with a CO ester, but we started with two equivalents of sodium ethoxide. So as we've seen in the examples before, if we have sodium ethoxide and there is still one alpha hydrogen, it will be deprotonated. So the next step is the deprotonation of this of the alpha. So A, B, C, and this is carbon D with the BR. So as you can see, the difference in here that the other alkyl halide is still in the same molecule. So the molecule, it's an intramolecular reaction in which the molecule is going to be reacting with itself. So this will attack this one, which is a primary, not tertiary, not phenyl, not venyl. The result of that, we didn't see this yet before, but we know that every time we're doing an intramolecular, we're ending up with a cycle. So this is carbon A, carbon B, carbon C, carbon D. Now adding H3O plus heat, the usual is the 2-ethanol plus CO2, the usual, then 1 carboxylic acid. It's alpha carbon, which is I'm drawing in the same color with an H. So the end result of this is a cyclic compound, and another way to draw it, if you'd like to, is to draw it this way. So this is the carboxylic acid, this is the alpha carbon of the malonic ester. These are the A, B, C, D. So how you can figure that out, it should be like very typical from now on because you're gonna see it often. If you have two equivalent sodium ethoxide and you have an alkyl halide that it has dialkyl, you're expecting a cyclic compound with a carboxylic acid attached to the alpha carbon. Now there is a trick that I use it myself to kind of as my check and balance whether I'm doing it right or not. If the BRs are 1, 2, 3, 4 from each other, it's going to be a 5-member ring. Why? Because it's always, there will be the alpha carbon that is attached now to both of the carbons of the BR. If the two BRs or two CLs or two Is are 1,5 from each other and I'm doing malonic ester, that's very typical 3 steps, it will be a 6-member ring. Why? The 5 carbons of the dialkyl and the alpha carbon added to them to form the cycle. 1, 7, 8-member ring, and the carboxylic acid attached from the alpha carbon. And by the way, in the chapter 20, I didn't discuss how we prepare carboxylic acid, cyclic carboxylic acid, where the carboxylic acid is attached to a cycle, and this is the way we do it. Okay? Does this make sense to you, how to spot it, or even how to figure out the starting material? Go ahead.
What do you do if you get the same thing as number 2, but it's not symmetrical? Would you only protonate 1?
All right, great question. So she's asking, what if there is a methyl attached to this one or to this one? It's going to be exactly the same. The difference is when you call AB On carbon B, it will be attached to the methyl or to the ethyl, but they will be equivalent. Now, if your question, what if they aren't equivalent? The one that is like the less sterically hindered will react first and fast, then the second one, as long as it isn't tertiary phenyl or vinyl. The end result is exactly the same. It's which reacts first and fast. Did I answer your question? Okay, so now we're done from these dicarbonyl, malonic ester, acetoacetic ester. The one thing that we didn't discuss yet is what if I have an ester or a nitrile and I add LDATHF? Do these have an alpha carbon that can be deprotonated, an alpha hydrogen that can be deprotonated? And the answer is yes. If you have a monoester or a mononitrile or a monoketone, you use exactly the same stuff. For example, if I have, this is an ester and it is cyclic, so we refer sometimes to it as lactones. If I add LDA, THF minus 78 Celsius, I'm gonna deprotonate the alpha carbon. The question is A or D the alpha carbon? Is carbon A or carbon D the alpha carbon in this case? Go ahead. Very good. It's A, because the carboanion, for it to be the alpha, the carboanion should be close to the carbonyl. So the first step will result in the deprotonation, the formation of the carboanion. The next step, adding iodomethane, not tertiary, not phenyl, not vinyl, exactly the same rules, will result in the alkylation of the alpha carbon of the ester. In other words, whatever applies to a ketone applies to a cyclic ester or an open ester. But clearly I need to use the LDA because it is a stronger base than the ethoxide. Now the same case is for a nitrile. If I have an RC triple bond N, let's see an example of that. So let's say I have this nitrile in here and I added LDA, THF, minus 78 Celsius. Now the alpha carbon in this case is this. Consider this the carbon of the carbonyl, the same as the carbon of the carbonyl, and the nitrogen as if it is the oxygen. And that would result in the deprotonation of this. Now I'm gonna stop for a minute and discuss, is really that alpha hydrogen acidic? Is it an acidic alpha hydrogen, the same as the ketone one? If yes, why? And if no, why? Yes, it is an acidic one. Why? It's close to a withdrawing group, right? The same as the carbonyl. And it also has a resonance, right? This lone pair is one single bond from the triple bond. So it has exactly the same kind of stability as that of a ketone with the resonance structure and the carbanion. So the next step is CH3I, which is also not phenyl, not vinyl, not tertiary. So as you can figure out, it's exactly the same as the idea as that of a monoketone. Now, one thing about that is I have to remind you that the nitrile has two reactions that it can undergo. The first one, if I add H3O plus heat, I can change the nitrile to carboxylic acid, or I can reduce it to end up CH2 and H2, which is the primary amine. So I'm just reminding you that whenever there is a nitrile, there is a possibility of hydrolysis to go to the carboxylic acid or reduction to go to the amine. Does this make sense, guys? So in other words, this alpha alkylation can happen to esters, to cyclic esters, to malonic ester, to acetoacetic ester. to ketones, to aldehydes, as long as there is an alpha hydrogen on the alpha carbon. So, in here we're starting with the acetoacetic ester, ending up with this compound. The question is, what are the steps needed to achieve this change or this transformation? Stop the video right here. Okay. We're starting with acetoacetic ester. We're ending up with a tertiary alcohol. And the usual 3 steps should end me up with a methyl ketone with its alpha carbon something attached to it, which I can't see directly. But I know that tertiary alcohols can be prepared from ketones. So I can predict that this COH, or the carbon that has the OH, used to be a carbon of the carbonyl. So I'm going to say, okay, let's map it. This is the methyl, this methyl. This carbon used to be the carbon of the carbonyl of the 3 typical steps. This is the alpha. I'm going to choose this is to be my alpha, and whatever attached to it is the alkyl halide. So I'm going to do these 3 typical steps: sodium ethoxide and iodomethane. I figured that out from the mapping I've done. And the third, H3O plus heat. So I'm going to end up with this in here. And the methyl, which I want, if I want to map it, is this one in here. So comparing these two now, the carbon, we know that the carbon of the carbonyl is now the carbon of the OH. So this in here is this in here. So whatever left, I can think about it. What are the reactions from chapter 19 that we learned that I can add carbon to a ketone? It's either Grignard or Wittig. Grignard will give me, if I'm starting with a ketone, I'll end up with a tertiary alcohol. So if this is my ketone, whatever left in here is my alkyl halide of the Grignard. So what I'm gonna use is this is to prepare the Grignard, followed by H3O plus at 0 Celsius. So this is how I can prepare this one. So this is what I mentioned earlier, that sometimes we might do one more step other than this after the 3 typical steps. So always keep an open eye that if you're starting with acetoacetic ester and you don't see a methyl ketone in the answer, that might be 1 reaction or 2 reactions more to get there. Does this make sense to you guys? Questions about anything I've done in here? Okay, let's do some more practice on this. Okay, so in here, I'm starting with this nitrile, ending up with this compound in here. The question is, what are the steps necessary to go from the starting material to the end material? So we're starting with this compound in here, which is a nitrile. Looking at the end material, I see a primary amine. This is the point where I should identify that this is a primary amine. Usually the reduction of a C triple bond N always end up with a CH2 and H2. So I'm mapping it back saying, okay, this and this are these 2 in here after reduction. I don't know when I'm going to do the reduction, but there is reduction that need to be done. Now, after that, I can say, okay, this is the nitrile, this is its alpha carbon, this is the benzene ring. So this part in here is this part of the molecule. So I can see on the alpha carbon, there is this group attached to it. So the question is, should I do the reduction first, then the alpha alkylation, or the alpha alkylation first, then the reduction? And here where I see most of the student trip in the exam trip of whether in the exam or the practice exam or OWL. If I reduce, would the alpha carbon be acidic anymore? No. So the first step is to attach the alkyl into the alpha, then do the reduction. So the first step is I'm going to use the LDA THF minus 78. Can I use sodium ethoxide for this one? For nitriles, esters, and monoketone, can I use ethoxide? No, I need to use the LDA. Followed by, clearly I identified what I circled in green as the alkyl halide. Is this alkyl halide phenyl-venyl or phenyl-venyl or tertiary? No, so this is a benzyl, so the reaction can take place. Attaching it, I'm gonna keep the color coding for you. So if I added lithium aluminum hydride as a next step and H2O, this will be reduced to CH2 and H2. In other words, I can add to the alpha whatever I want as long as it isn't tertiary vinyl or phenyl, and then I can do the reduction or the hydrolysis, either or. So anytime you see a primary amine and you can see that the alpha is substituted, this is the method. First the substitution, then the reduction. Does this make sense? Questions? And I think, so we're gonna stop right here. Enjoy the rest of your day and I'll see you tomorrow.